Okay, yeah, let's get started. So, as always, we'll do some logistics, just to get that out of the way. So, a quick update on homework 4. There have been some, pretty weird issues with the auto grader. So, likely what's going to happen is that we're going to grade homework 4 manually. What that means from your end, as long as things are working locally for you and you run everything and things seem to make sense, you shouldn't have anything to worry about. We'll be grading it pretty leniently. So when you submit to the auto grader, you might get a score 5 out of 100 or something like that. Don't worry about it. It's just you won't see any test cases run. So just be aware of that. As far as project goes, so the project proposal should have been returned to you on Gradescope. So if you go to that and click on your assignment, you should be able to see a decent amount of comments. These comments range anywhere from pointing out things that we think are good ideas about your project, or giving you some suggestions, or just questions for you to think about. I highly encourage just referring to those comments. If you've already started, that's great. You can take the feedback and maybe shape your project as you go along. And if you haven't started, then this might give you some ideas of what to think about as you begin. The next due date for the project is on the 21st. So that'll be your checkpoint. We expect around 75% completion. So whatever that means to you, make sure it's done by then, just to make sure you're staying on track with things. And then if you think that your project vision is changing, what you're planning on doing doesn't match whatever you put in the proposal, please let us know. You can just write an email or something, and it could be very quick, just so that way we're on the same page and can give you feedback regarding those updates. Also regarding homework 4, that's due on Monday. Any questions regarding homework 4, the project? All right. So today we're going back to SAT world. It's been a few weeks since we've talked about this. We're going to revisit it today, but we're going to relate it to constraint programming. So the main question that'll be motivating today's lecture is, how does constraint programming relate to SAT? So before we get into all of that, there's just a little bit of prerequisite information or stuff that we've covered in the past that we want to recall, just so that way it's at the forefront of our minds. I should probably find a marker. There's a couple markers over there. So as I'm getting a marker, you might remember this picture from maybe it was last week or the week before, where it was just showing the space of linear programming, integer linear programming, mixed integer programming, and then we took the step out to constraint programming world. Both things are garbage. So my question is, where does SAT fit into this diagram? If you were to draw a new circle representing SAT, where would you draw it? And just to make sure this diagram is kind of makes sense, the reason why, for example, integer linear programming is within mixed integer programming is because I can write an instance of an integer linear program as a mixed integer program. I just say that everything has to be an integer. But LP and ILP aren't overlapping because you can't really write one as an instance of the other. So where would SAT fit into this?
Would it be inside ILP?
Inside ILP. So why? Any idea why that might be the case?
Because I guess you could write the constraints as 0 to 1.
Okay.
Outside CPU, CPU would fit inside SAT.
So it should contain everything. And why that?
Because we've discussed that the constraint programmer is solving CP by converting it to an instance of SAT and then solving the SAT problem. So then it should.
Mm-hmm. Any other ideas? Yeah, well, the answer is there's not really a great answer. So the way I've drawn it like this is like this, where it's like, it has some elements of constraint programming. It also has some elements of mixed integer programming, and maybe it should go into integer linear programming because that's kind of like the part that it overlaps with mixed integer programming. So, that's correct too. So in essence, it's like both of your answers combined in a way that it has some similarities to constraint programming because, after all, we're solving a program subject to constraints, namely each clause has to have one true assignment or at least one true assignment. But it may not be immediately clear how this all relates together. So this is maybe the visual to keep in mind. Yeah.
Does it mean that there are instances of constraint programming problems that cannot be converted to instances of SAT?
I'm not too sure about that.
Because then otherwise it would just be an overlap thing,
Right. Yes. Like I wouldn't say that this diagram is accurate just because we can argue so many different ways. It's just like it has some overlap. But yeah, I think you should be able to convert CP to SAT for the most part. Okay. Any other questions regarding this? All right. So a loose analogy that we can kind of think about things, everything that we've talked about thus far, and how it maybe relates to a computer. Constraint programming, which is what we've been talking about recently, you can think about this as like a high-level programming language. You're typing the stuff, and it's like pretty simple to write in words what your constraints are. But of course, the computer needs to solve it. So our tool CP-SAT, you can think of that as the compiler. It's going to convert our constraint program into something that the computer might understand. And what we've been saying is that it converts it into an instance of SAT. So if that's the case, the SAT formula, you can think of that as the assembly language. It's sort of what the computer is understanding. And then lastly, we had our SAT solver. So that's like the actual hardware carrying out the task of returning the answer. So that's just drawing comparisons between things. So today we'll discuss how CP-SAT actually converts constraint programming into SAT formulas. But it turns out that this thing that I've been saying that, it just converts it into SAT is kind of wrong. It's a little bit of a lie. It's not so simple as CP-SAT sees a constraint and then it encodes it as a clause. It's a little bit more of a conversation, or there's a little bit more to it. So we'll talk a lot about that today. And this is also active research. So improvements are being made on this. And if I make any mistakes in this, then that's my fault, but just good to keep in mind. So the other thing that we want to recall before getting into the meat and potatoes of this lecture is CDCL, which stands for conflict-driven clause learning. We talked about this around 6 or 7 weeks ago. Does anyone remember anything about CDCL? What it was, what goes into it?
CDCL, where like if you know a particular solution of a SAT problem, then you can add the clause that is showing that at least one of them should be different from like that original one, so you get a different answer, or like you know that original one was the only answer that you have.
Yeah. It was this idea of like, let's solve SAT, and as we find a conflict, we will add a new clause to our formula, so that way when we back jump or backtrack, we won't make the same mistakes over and over again. So, this is the code that we had for it. So it was essentially like the simple backtracking where, we're choosing a variable, then we'll set it equal to true. We had that unit propagation element to it. What was unit propagation? Someone else. Unit propagation in SAT solver. Urush?
It's kind of like if there's only one valid value left for a given literal and a clause,
Mm-hmm.
then you assign that literal.
Exactly, yeah. If we had a clause that was like x1 or x2 or x3, and we said that this one is false and this one is false, then our SAT solver would immediately set x3 equal to true because that was necessary. Great, so we check for unit propagation. Then we basically checked if we had a conflict, let's analyze the conflict, and then we would back jump to a point where we didn't have a conflict. And we would add onto the formula a conflict clause. So we might remember this diagram or this example that we went through where you make a bunch of decisions that imply other things to happen, usually with unit propagation. We would get a conflict, and then we would draw a cut in our implication graph. And this would give us a conflict set. We would look at the edges that cross this cut and where they start from, and that would give us the conflict set. And then we would add a conflict clause, or like a learned clause, where we would negate those variables that contributed to this conflict. That was the clause that we learned. And then when we would back jump, we wouldn't make the same mistake twice. Remember this? Kind of, maybe. All right, good. So, yeah, like I said, this content is active research. It's a little bit complex. Do your best to stay with it, but if not, well, whatever. So when we've been talking about constraint programming, we've been saying that our variables are integer quantities. We said, they can't be decimals, it's only integers, and they had their own finite domains. Right? We would say like new int var, and then the lower bound and the upper bound, and this would form a finite range. So before we get into how CP relates to SAT, how CP SAT works, we're going to understand something called finite domain solvers. What is that? Well, I don't know, let's figure it out. So the way that CP solvers work, as well as these finite domain solvers work, is that there's going to be a domain that is held for each variable, right? So when we define a new variable x, and its lower bound and upper bound, this is just saying that the domain of x is going to be lower bound to upper bound. It's just the different values that a variable can take on. And, okay, so we'll have a bit of notation. Min sub d of x is the minimum value that a variable x can take on its domain, and max is the same thing, except for maximum. So that'll be our notation there. And so the idea is, like, as we're solving constraint programs, we want to ensure that when we assign a variable to a specific value, other variables can be assigned to their values in a way that matches what we've defined. So if I have a new variable y, which is new int var, and maybe it's just 0 to 2, and if my solver suggests that let's set x equal to lower bound plus 3, and that implies to us that y, for whatever reason, has to be 3 due to some constraints, that wouldn't be good. Our solver shouldn't like that, because we would never want to assign y equal to 3. So our solver needs a way of maintaining bounds consistency. That is, having domains for each variables such that if I were to make an assignment to a variable within the domain, I am able to find an assignment to another variable or to the other variables that is still within their domains. I'll pause if there are any questions. All right, so for definition, we'll introduce this term bounds consistent. And so we'll say that a set of variables, as well as a constraint C, is bounds consistent for a variable, or for a domain, if when we take each variable and set it to the minimum value in its domain, or when we set it to the maximum value in its domain, we're able to find assignments of other variables within their domains that satisfies the constraint. So as a non-example, let's say we have these three variables with their respective domains, and we have a constraint x equals y plus z. To see if this is bounds consistent, we would take a variable, let's say x, and set it to the minimum, in this case 4. Now we need to check, can we find a value for y and a value for z, both of which within their domains, that satisfies the constraint? And in this first case, we can. Y equals 4, z equals 0, 4 plus 0 does equal x equal to 4. Then we test when x is equal to the maximum value, 7. And again, we can find y and z within their respective domains that satisfies it. But when we test y equal to 1, its lower bound, suppose we choose x equal to 4, we can't find a z in the domain that satisfies the equation, because we would have 4 equals 1 plus z, z would need to be equal to 3, that's outside of its domain. And if you were to try something else for x, maybe like 5 or 6 or 7, same issue. You wouldn't find something for y or for z in its domain. So this example is not bounds consistent. Does it make sense? Kind of? Okay. This should kind of explain some motivation as to why we're talking about this, because our CPSAT solver, when it assigns a variable, we want to make sure we can find other variables, that other variables have an assignment to them that still works. So here is an example of something that's bounds consistent. It's identical to this last example. The only thing that's changed is this domain for y. Originally it's 1 to 5, now it's 2 to 5. That's all we've changed. Now, once you test the lower bound and upper bound for each variable, you can always find other variables have a value within their domain that satisfies it. So, why is this important? Ideally, if we were to feed, this into our constraint program, maybe this is a program we want to solve. We have specific variables with their domains, we have this constraint. We would want our CPSAT solver to know that this doesn't work. But if you can find a way of creating these domains, then you have nothing to worry about, because a solution will still exist. So we want a way of updating our domains to ensure we can find a solution. All right, let's see. Where am I in my notes? Somewhere here. So now here's a new term called propagators. Sounds familiar? Yeah, it probably should. This is a little bit more complex in terms of the words describing it, but in actuality, it's a pretty simple thing. So the word-for-word definition, a propagator for a constraint C is an algorithm or a process that also has a domain D, and it will return a new domain, D prime, where C is bounds consistent with D prime. So what that means is a propagator would take this, domains with a constraint, and it is some sort of process that would give us a new domain that is bounds consistent. So the propagator is going to be the word that we use to just describe me clicking the slide to get us something that works. So that's what a propagator is. Additionally, a propagator will give us explanations, implications that are explanations that explain the updated bounds in D prime. So a propagator would tell us, because of some reasons, I cannot have y equal to 1, therefore I am setting y's lower bound equal to 2. So a propagator will also give us that implication with it, and we'll see it in just a moment. Any questions on what a propagator is or anything I've talked about thus far? So let's see a propagator for this. Instead of me just clicking the switch, let's actually see a propagator. So the way we would kind of do this by hand, this looks really ugly, and it is. It's just saying, let's ignore the domain for now. Let's just look at the constraint, in this case, x equals y plus z, and just isolate each variable. And now we can kind of like make some assumptions that the smallest that x can be is equal to the smallest value of y plus the smallest value of z, ignoring domains altogether. If I gave you x, y, and z, and I said x equals y plus z, and I told you y is at least 1 and z is at least 1, you would say x is at least 2, because those are the smallest values of y and z. Similarly, the upper bound, x cannot exceed the maximum value of y plus the maximum value of z. This is like, I don't know, 6th grade math or something. It just looks super, super ugly here. So we're just sort of bounding our variables based off of the constraint. Well then, once we reconsider our domains, as well as these bounds that we've considered, on the previous slide we said y must be greater than or equal to the minimum value of x minus the maximum value of z. When we consider the domains and we plug those values in, we say y must be greater than or equal to 2. So that is the propagator right there, saying that this is the update I'm making. I must have y greater than or equal to 2. And so I will give you an explanation that since x is greater than or equal to 4, or like when x is greater than or equal to 4 and z is less than or equal to 2, y is greater than or equal to 2. So propagator did that update and gave us this implication right here. This is pretty good news. This is really good news because we have a tool that can ensure that we'll still find a solution by updating our domains. And on top of that, it tells us what it's doing. And even better, if our end goal is SAT, where we want clauses, dude, that looks like a clause almost. There's a logical and in there, and there's an implication, and we know we can break apart the implication into other things. Like that's darn close to a SAT clause. So it seems pretty simple, and maybe a little bit is kind of like swept under the rug of like, oh, how does it go about explaining it? But like, this is pretty good news. Questions? All right, where am I here? Okay, so the way constraint programming solvers work is basically using whatever we talked about. You take the domain that was specified by the user, and then you introduce a new constraint. That could be a constraint specified, or it could be assigning a variable to something, because that's something our solver has to do. Then we run our propagators. We'll like update our domains. And if it happens that there's a conflict, meaning our domain has updated in a way that there are no values left for a single variable, that's an issue. So we will backtrack. And we can add the opposite of the constraint. Otherwise, nothing changes, and we can add another constraint and repeat. What does this sound like? What does this process sound and feel like? Where you make a decision or add a new constraint, you run propagators. If there's a conflict, you backtrack. Otherwise, you keep on going. CDCL, yeah. Or like DPLL. That's just whatever we did for SAT. Right? It's the same exact motif. So, okay, before we get into that, let's just see an example of it like fully. So, a new example. We have 5 variables. All of them have the same domain, 1 through 4. we have a bunch of constraints. First, x2 is less than or equal to x5, x1 through x4 have to be different values, and the sum of the first four have to be less than or equal to 9. And we're going to, at a very high level, simulate what a CP solver might do. So, remember, our CP solver is going to be responsible for updating the domains, as we've been talking about, and we'll see that in action. It's also responsible for figuring out what the values of our variables are, right? Because we're using a CP solver to get our answer. So it's going to try to make decisions of setting variables equals to numbers. So maybe the first decision it makes is, let me set x1 equal to 1, and let us see what will happen. So in that case, we'll track the domains of all of the variables. If I make this decision, then the domain of x1 is just equal to 1, because that's the variable I've set it to. Now, our process here said that, okay, let's add a new constraint and see what happens. So maybe we choose this constraint, all different x1, x2, x3, x4. So our solver is going to update our bounds. It's going to do that propagation. Since x1 is equal to 1, I cannot have x2, x3, or x4 be equal to 1. So I'm removing that value from the domain altogether. I'm essentially updating it. So this is essentially making sure things are bounds consistent, but in another sense, it's just making sure things make sense, right? I don't want x2 to be equal to 1, so let me remove 1 from its domain. Make sense here? Okay. Now we would check if there are any conflicts, and in this case there would be, because when we consider this constraint, x2 is less than or equal to x5, in the previous iteration, that wouldn't always be satisfied, because we could have x5 equal to 1 and x2 equal to something larger than that. So when we consider this constraint, we need to update the bounds accordingly. So in this case, since x2 is at least 2, the lower bound for 5 must also be 2. And sure, you might say that, well, isn't it possible for x2 to be equal to 3 and x5 to be equal to 2? And that would break the constraint. Yes, but I don't care. Because this bounds consistency just said that I need to be able to find some solution that works. I need to be able to find just one thing within these domains that satisfies everything. So it's just keeping our options open, but updating our domains accordingly. Okay. Now, we would check, are any constraints broken? In other words, are there any constraints for which there is a potential of, that's not even good. Okay. Anyways, basically, we could check all of our other constraints, and they all could be satisfied with these domains here. Right? x2 is less than or equal to x5. That is possible to satisfy with these domains. All different, x1, x2, x3, x4. That's possible. For example, this is 1, this could be 2, this could be 3, this could be 4. And then the sum less than or equal to 9, 1, 2, 2, 2. So we're just thinking about constraints individually. Don't worry about how they tie together. So if that's the case, we would continue. Our constraint program would then, make a new decision, whether that be assigning a new variable to a new value, or maybe it chooses to bound a variable, right? So these decisions that we're making, we'll kind of treat them as a black box of what the constraint programming solver is doing in its own mind. We'll just track how the bounds update. So here, x5 is less than or equal to 2. We would refer to our bound from before. That doesn't work because it could be 4 here. So we'll update it accordingly and say that x5 has to be equal to 2. Okay. I believe the next thing it checks for is x2 less than or equal to x5. So if that's the case, what would we expect the next column to look like? How would the domains change when we say x2 is less than or equal to x5? I'll give like a moment to think because it's a little complex.
X2 has to be 2.
X2 has to be 2. Ishaan, do you have a different idea?
Same.
Any other ideas? Yeah, exactly. Just updating the bounds accordingly. Okay. Are there any constraints that could be potentially violated? Okay. The next thing it would check is like x1 plus x2 plus x3 plus x4 if that's less than or equal to 9. Or no, sorry, not that one. It would check for the all different constraint. So if it were to test all different, how do we need the bounds to update accordingly? Because right now, for example, like x1 is 1, x2 is 2, those who are different, we need to make sure that we're not assigning these two to something that's already been assigned.
I would change x3, x4 to have only from 3 to 4.
Exactly. We don't want them to be 2. Let's extract 2 out of their domain. Okay. Now, next we would check if the sum is less than or equal to 9. So basically it would see that, okay, if I had 4 for both of these, that wouldn't be good because then the sum would exceed 9. So it's extracting 4 from its domain, leaving us with just 3. Because now when I sum these together, it's less than or equal to 9, which is good. So we've gone through all of the constraints. That doesn't mean anything. Because as we update a constraint, its domains are changing, which means other constraints could be violated. I mean, is there any constraint out of these 3 that seems to be violated if these are the domains of our variables? Yeah. All different, right? These 2 are the same. No good. So, we would consider that constraint. We would update the domain accordingly, which basically we would have to remove 3 from both of these domains.
Why would you remove it from both?
Well, okay, you could remove it from one. Regardless, one of these is going to be an empty set. We're going to have an empty domain. That's not good for our solver, because our solver has to assign values to our variables within the domain. So, we reach a conflict. We would backtrack or back jump and change things accordingly. Maybe we would, here I guess we're updating this to 3 and then seeing what would happen. So it's very similar to CDCL, very similar to DPLL, where we're making decisions, having some sort of propagation. Instead of assigning variables to true, we are updating domains. Then we check if there's a conflict. If so, backtrack. Questions on any of that? All right. So, just to highlight this comparison, adding a constraint is very similar to making a decision as we did with SAT solving. Remember, this was like setting x1 equal to true. Running our constraint propagators is very similar to unit propagation. Backtracking, well, that's just backtracking. So why would we go through the hassle of trying to, introduce these domains and updating the domains accordingly if it's so similar to SAT? Why don't we just take a constraint program and write it as SAT? Why wasn't that my first lecture where I gave you CP and I'm like, here's how you convert it to SAT? Why haven't we done that? What could go wrong? Well, here's a first question to think about. What would be the Boolean variables? Please remember, where's the eraser? In CP world, we have our variables, and they each come from their own domain, which is some sort of integer interval, lower bound to upper bound. But in SAT world, our variables only come from the set 0 to 1. So we need to come up with variables that are Boolean variables, like that, if we were to write CP as SAT. So what would some guesses be as to what our, variables could be? Suppose I had I'll just give an example. Let's just say x is a variable here, and it's within the bounds 0 to 10. It's a difficult question, but that's why any answers are good answers. Michael?
Variable for each of x is equal to each value of an its domain.
Yeah. There is something I wanted to mention before I ask this question, but I'll mention it after I ask you why you think this could be a good idea.
I don't know if it's the best idea, but it looks like it could work.
Yeah. Okay. So the thing I wanted to mention is that in CP world, our solution, when we give it to the solver, it returns to us an answer, like x1 equal to 7, x2 equal to 6, etc., etc. It gives us the value for each variable. In SAT world, it just tells us something like x1 is equal to true, x2 is equal to false, etc., etc. So if we were to try to draw a comparison between these two things, Michael's idea is pretty good. Have a variable for each one of these, and when we feed it into our SAT solver somehow, maybe this gets assigned true, and everything else is false. And that would tell us, okay, x equals to 7. That's a really good idea. Turns out it's actually not. And here's why. The biggest issue is that we're going to have a massive amount of variables. Like 0 to 10 is fine because we'll just have 11 variables. But if this was like 1,000, we're going to have a lot of variables. Yeah.
Can you represent the bits of x instead?
Yes. So attempt 2 would be to basically do a bit encoding of each variable. And it turns out both of these ideas, even though they're very, very smart, they both have their issues. So with this first idea is we have a ton of variables, which isn't necessarily a bad thing. But if our SAT solver uses unit propagation, and we have a lot of variables making our clauses very, very long, it could be a lot harder to propagate. For example, if we wanted to encode x is less than or equal to 10, our thing would look like x is equal to 0, or x is equal to 1, or x equal to 2, all the way up to here. And if we were to attempt unit propagation with our solver, we would need a lot of things evaluated to false. So we would say it has poor propagation strength, because that's not super likely to happen. And then for the logarithmic encoding, it fixes the issue of too many variables. It just turns out that the propagation strength is even worse. I mean, you can try to devise a way of encoding x is less than or equal to 10 with the bit representation, but since there's a non-intuitive way of doing it, or the intuitive way requires a lot of variables, the propagation strength wouldn't be super great. So, both of these attempts, like I said, very smart. Great that you both came up with it. That's amazing. The solution that we'll end up using will accept the fact that we're going to create a lot of variables, but it will fix our propagation issue slightly. So we'll create essentially 2 variables. So for each value in our domain, we will create a variable x is equal to that value, etc., etc., essentially using Michael's idea. But we'll also add a new variable, which tells us if our variable is less than or equal to that value. Now we can encode that x is less than or equal to 10 constraint a lot easier. But this will be helpful. And you can represent greater than or equal to and not equal to just by negating the two variables. But in addition to all of this, we're going to add a bit of consistency, just logic that we know holds true, but we need to encode. For example, if x is less than or equal to I, if this variable is true, then x is less than or equal to I plus 1. That must also be true. So by throwing in that implication, it would ensure that this gets set to true when the left-hand side is true. And then if x is equal to I, that's a by implication with it's less than or equal to I, but it is not less than or equal to I minus 1. So lots of variables. It's still linear in the size of the domain. But with this, the propagation strength is a little bit better. So it's just enhancing Michael's idea. Chris, I'm not sure if we can enhance your idea. I'm sure it might be possible. I just didn't research that, but I should have done that. Okay, so let me just write this constraint on the board. So that's our constraint. And these are your variables. Encode this constraint using your variables. How would you do it? I'll just write variables x equal to I and x is less than or equal to I. How would you encode this constraint? And you can talk to your neighbor if you want to, because it's a pretty ugly question.
What are the bounds of each variable?
Yeah. Okay.
This is a question about the previous slide.
Mhm.
So you have double the amount of variables with a bunch of redundancy, but it allows you to propagate better.
Yes.
Okay.
Yeah. So we conceive defeat. We accept defeat with the amount of variables, but we will take a lot of variables if we can improve propagation speed. Any ideas of how we might write this constraint? Alex, you seem like you have an idea.
No.
Try. What are you thinking?
Can we assume they're all positive or no?
No. It's a hard question. It's a very hard question. I'm sorry I put you on the spot. All right, I'll give it because everyone's had a long day, including me. So we'll add the following clauses. And the idea is just we'll isolate for each variable. And we'll say that, hey, if my solver seems to set y equal to some value I and z equal to j, then I need to tell my solver that x is equal to I plus j. That is something that must occur. So we would add this implication into things. But also for the other variables, if our solver seems to set x equal to I and z equal to j, that means y has to be equal to I minus j. And same for the last one. So we would add all of these three things, and I and j are coming from our domain. This poses an interesting question. Namely, how many clauses are we adding, or how many implications are we adding? A lot. We already said that this difference can be a lot, upward, maybe 1,000, and now we're squaring it. We're adding a lot of clauses, which is not good. And this is only for this example. If we added more variables, if we summed more variables together in the constraint, the amount of clauses would blow up exponentially. That's not great. So how do we solve this issue? It's not an easy question. So this introduces something called lazy clause generation. And the idea behind this is that even though a constraint will introduce a lot of clauses, as we just saw in the previous slide, most of these clauses are never used. Right? You can think about it. All of these is if x is equal to some value and z is equal to some value, then something else happens. It's pretty unlikely our solver is testing all of the different values of x, y, and z. It might just be testing some. So there's a lot of clauses that will go to waste, a lot of those implications that will go to waste. So LZG, lazy clause generation, says that instead of just taking the constraints and writing a bunch of clauses, a bunch of implications, and shoving that into our solver, we'll just sort of generate the ones that we need when we need them, on the fly. Which sounds too good to be true. It just sounds like, can we even say that? And the answer is like, well, maybe. I don't really know, honestly. So, what time is it? Good. Okay, good. We'll be done soon. The key thing that we have to recall is when we did the finite domain solver propagation like 30 minutes ago, we said that our propagators give us an implication, an explanation of what it's doing. And as I mentioned, it's pretty easy to represent these things as clauses. So we will run our solver, do our propagations, and then as we find these explanations, we'll sort of add it into our entire worldview. And I think it's best seen with an example, not the pseudocode, but it's here if you want. We can go through it quickly, but it's pretty much CDCL. The main thing here is that when we do a propagation and it reaches a conflict, and this is the propagation right here, where basically once we find the conflict, we'll find the explanatory clause, like the implications that cause the conflict. We'll sort of just add that into our formula, very similar to what we did for CDCL. So this is the walkthrough example. It's the same thing as before. We're going to draw our implication graph, very similar to what we did for CDCL. So maybe the first decision we make is set x1 equal to 1. Then we would run our propagation, and basically the constraint all different for these would tell us that, okay, x2 can't be equal to 1, x3 can't be equal to 1, x4 can't be equal to 1. So I would update my domain accordingly. These three must be greater than or equal to 2. So whatever we saw a few slides ago with the yellow boxes and each column was a new thing, we're just doing that, just representing it as a graph, where these arrows or the edges are the implications. So now we would consider a new constraint, something that's potentially broken. So the constraint said that x2 is less than or equal to x5. Well, if x2 is greater than or equal to 2, that means x5 has to be greater than or equal to 2. It's the same thing we saw before, just in graphical form. Okay, then a new decision is made. x5 less than or equal to 2, for example. Well, this decision, tied together with information we have about the domain prior, together they tell us that x5 has to be equal to 2. We're updating the domain based off of prior information. Then we would check our constraints. Is anything potentially violated? So we would check maybe x2 is less than or equal to x5. And since x5 is less than or equal to 2, x2 has to be less than or equal to 2. Just as a consequence of this decision and our constraint right there. And as we're going along, we're getting these implications. And then again, you would propagate consistency. So since we said earlier x2 is greater than or equal to 2, and now we said x2 is less than or equal to 2, together that tells us that x2 should be equal to 2. And okay, I think that was already there. And then we would keep going. Consider more constraints, see if things are violated. If this thing is 2, those two both can't be equal to 2. So we would say they're both greater than or equal to 3. It literally maps to the previous example we did with the charts. So if it's confusing, you can compare the two. And then you keep going. Check the sum. That's when we removed 4 from the domains. So we're saying, okay, it's less than or equal to 3. These tied together with this tell us that the values must be equal to 3. Then I think we checked all different. Yes, we did. And that led us to a conflict, right? Whatever I explained in words now, as well as 20 minutes ago, is just as a graph. You can trace the edges, and it gives you those explanations. So we've reached a conflict, and as we did in CDCL, you would find that cut, and we won't worry about reviewing how you find the cut, but you might remember UIPs, the unique implication points, and draw a cut there, and then you would look at the edges that cross the cut and see where they come from. So in this case, we have these two edges come from this variable, this edge comes from that variable, that edge comes from that variable, that from that, and the bottom one from here. So those are the vertices of importance, and together they would give us that learned clause. When we did CDCL, we looked at those vertices, those nodes that had variables and their truth values, and the learned clause we added was the negation of all of them. We're doing the exact same thing. That these, whatever the emanation point is, those things together contributed to a conflict. Therefore, I don't want to see this conflict in the future. So I will add this clause to ensure that I never make the same decisions that got there. And then we would back jump to the asserting level. Same thing as CDCL. Make sense? Questions? And then you keep going, right? You add the clause and keep going. I'm not going to talk about these slides just because they're not super important, but they're there if you're interested. The idea is that as we go, we can delete explanations as we go along. But I won't talk about it. There's also something called lazy Boolean variable creation. It's kind of what it sounds like. Instead of creating the constraints or the clauses when we need them, now we're creating variables when we need them. So it kind of fixes the issue of too many variables. And then there's a whole bunch of talk about how you would encode it, but I think that's pretty boring. And then you can read this if you want to, but I'm not going to cover it. So yes, pretty quick class today, but that's kind of how I wanted it to be. Before we go, I don't know what I have to say. Finish homework 4, work on your projects. Remember to update us if you're making changes, just so that way we're on the same page. And then next week we'll talk about ESP, traveling salesperson problem. That has a lot of applications and a lot of different problems. So that should hopefully be a little bit more exciting, a little bit more tangible than all of this random domain nonsense we've been talking about. Yeah, that's about it. If you have any questions, come talk to me. Otherwise, you're free to go. I'll see you next week.